Hi algebra students, and welcome to your second lesson video in our unit on polynomials. This lesson is going to focus on something called exponent rules. Before we get into what that is, I've got our review question for today, which says Olalekan and Moses are racing. Olalekan starts 100 meters ahead of the starting point and runs 1 meter per second. Moses starts from the beginning of the track and runs 3 meters per second. Write an inequality that you could use to find how long it would take for Moses to pass Olalekan. Go ahead and try that now. All right. In this problem, they gave us a big clue with the word inequality. That's going to tell me it's going to be a less than or a greater than sign. For our inequality, what are we trying to do? Well, we're trying to write an inequality where Moses passes Olalekan. Another way you can think of that is we are looking for Moses's distance to be greater than Olalekan's. If his distance is greater, that means he has passed Olalekan. Now I've written it like that to help me see what information should be on either side of my inequality and for me to see what inequality sign we want to use. We're using a greater than one. Once I've got this done, it helps me because all I have to do is fill in the numbers. So for Moses, what do I know about Moses? Well, Moses is starting from the beginning, which means he has no extra meters added to his distance. He's starting at 0, and he is running 3 meters per second. So I could represent his distance as 3s. He's running 3 meters every second, so his total distance is 3 times the number of seconds he's run. We want that to be greater than Olalekan's distance. Well, what do I know about him? Well, he starts 100 meters ahead of the starting point, and he's running 1 meter per second. So for Olalekan, I'm going to start by saying, well, he's got 100 meters that he's starting ahead of Moses, and then he is running 1 meter per second. So his distance is 100 plus 1s. To make it similar to what we did over here, that's showing 1 meter per second. With this, that's fine to write if you want that, but we know if the coefficient is 1, you normally don't see that. So I'm just going to take that off and say 100 plus s. I could have given you a second part to this question and asked how long does it take or what's the time where Moses passes Olalekan, but this question only asked you to write inequality. And that's what this is. That's our inequality to represent this. Now that our brains are all warmed up, we can go ahead and get started. We said the focus for today's lesson is going to be on simplifying using exponent rules. We've seen that word simplify a lot. It means you're taking something crazy in math and making it look simpler. So we're going to be doing that using rules about exponents. Before we get into some of our problems today, I want to quickly review some of the vocabulary you're going to hear in this unit, and specifically in this lesson. The first one, the name of this tiny little number here, it could be a 3, it could be any number. That little number there we call our exponent. So today we're talking about rules that have to do with that number. The part attached to the exponent, it could be a variable like it is here, it could be a number, but this part that's attached to the exponent we call the base. And then the last word we're going to hear a lot, this right here is an example of a monomial. We learned this word in Thursday's lesson. What is a monomial? A monomial is going to be a polynomial with only one term. Mon or mono means one. So an example could be x cubed. Another example could be something like 4a squared b to the 5th power. I know it's a monomial if we're not adding or subtracting anything else. There might be a coefficient, there might be more than one variable, but if it's all together, it's just one term, which means it's a monomial. These are the words you're going to hear a lot in today's lesson. We said we were going to look at simplifying using exponent rules. There are 4 different rules we're going to look at today. And for each of the rules, I'm not going to tell you what the rule is. You're going to tell me what the rule is. But what we're going to do each time is look at a couple examples, and you're going to use those examples to come up with the rule. So the first one is going to have to do with multiplying monomials. I've got 3 problems here. We're going to do the first 2 together, see if you notice a pattern, and then confirm that pattern with a third one. So to show you what I'm talking about, each of these is an example of a problem where you are multiplying two monomials together. Now there's a rule that exists that tells you what to do, but if you don't know that rule, it doesn't mean you're stuck. You just have to think about what this means here. When I say x cubed times x to the fourth power, what does that mean? Well, x cubed means you're multiplying x by itself 3 times. So x cubed means x times x times x. X to the fourth power, it's the same idea. It means you're multiplying x by itself 4 times. So that would be x times x times x times x. So something like x cubed times x to the fourth power means this. Well, we said we want to simplify today. This is not simplifying. This is expanding it. What would it look like if I wanted to simplify this using just one exponent? Well, here I'm multiplying x by itself 1, 2, 3, 4, 5, 6, 7 times. So that would be x to the 7th power. Now remember, we're looking for a pattern here. We're going to do one more. This time, instead of a variable as the base, I've got the number 2. I've got 2 cubed times 2 squared. What would that look like if I did the same thing? Well, 2 cubed means 2 times 2 times 2. 2 squared means 2 times 2. I could multiply that all together and get a number, but we're trying to see a pattern with the exponents. If I wanted to write this with an exponent, what exponent would I use? Well, there's 1, 2, 3, 4, 5. I'm multiplying 2 by itself 5 times, so that would be 2 to the 5th power. Now remember, our goal is to see, do you notice a pattern with the exponents? I don't want to have to do this step every single time. Do you see a pattern with what you could do with those exponents to get to the answer? Well, usually in class, someone tells me, I think we can add 3 plus 4 gives me 7, 3 plus 2 gives me 5. If we were adding, what would you expect this answer to be? If I add those exponents together, I'm thinking it's going to be y to the 4th power. Let's confirm by writing it out. Y squared is y times y. Another y squared is another y times y. That would give me y multiplied by itself 4 times, which is y to the 4th power. So that just like that, you have become a mathematician and discovered that first exponent rule. That first exponent rule says that when you multiply the same base, so if they're both y's or both 2's or both x's, you can add the exponents. What that means is from now on, you do not have to write it out like this. You can just add those exponents to jump right to that final answer. I think it helps to see where these rules come from so that it's not just you memorizing a rule. It means you actually understand what's going on. Now that we've got that first exponent rule, I've got these 3 for you to try. The first one says y to the 4th power times y to the 5th power. The next one says b to the 6th power times b. This one can be a little tricky for students. If you think about writing it out like we were just doing, b to the 6th power would be 6 b's. This right here would be 1 more b, which would leave you with a total of 7 b's that you're multiplying together. What that means is if you do not see an exponent on a variable, that exponent is 1. It's 1 because there's 1b. You're multiplying one of them. This last one here says write a problem where the product is z to the 12th power. In order to answer this, you need to know what the word product is. I'm going to help you out a little bit with that. Product is the name of an answer when you multiply. So here, the product is b to the 7th power. I'm asking you to give me a multiplication problem where this is the answer. There are a lot of correct answers for this question. For this one, as long as your exponents add up to 12, you are good to go. So you could have 6 and 6 because that adds to 12. You could have 10 and 2 because that adds to 12. In class, I've seen people have a lot of fun with it. They might have added, instead of 2 terms, they might have done 3. So you could maybe do something like that because all of those exponents add up to 12. Like I said, there are a ton of different options for this one. Now that we have seen this exponent rule for multiplication and gotten a little more practice with it, the next step is to make these problems more fun by adding more to them. So instead of just having a single variable as your monomial, sometimes your monomials have coefficients or numbers in front. Sometimes they'll have more than one variable in them. The idea for multiplying these is the same. We're still using that exponent rule you just learned, but there's more going on in the problem. For example, if I wanted to do 2x to the 4th power, y to the 5th power, times x cubed, y squared, in order to simplify that multiplication problem, we want to see what can you actually multiply together. We saw earlier that the bases need to be the same. What that means is I can multiply my x to the 4th power with x to the cubed. I can multiply x to the 4th power with x cubed. I can multiply my y to the 5th power with y squared. We're just matching up the things that are similar. In this problem, I also have a coefficient 2. There's no other number or coefficient for me to multiply that 2 with, so I can start by just copying my 2 down. When I multiply my x's together, remember we said it's similar to what you were doing before. You're still using that exponent rule that says you want to add 4 plus 3 to give you 7. You can also multiply your y's together. Same exponent rule as before. We can do 5 plus 2, which also gives us 7. And we get this as our final answer. That's what it looks like when you simplify using that exponent rule. Got one more we'll do together. What do you think this one here is going to be? Well, I would want to start off here by multiplying my 2 coefficients. 3 times -3 gives me -9. Then I can multiply my 2 g's together. G squared times g to the 4th power gives me g to the 6th power, because when you're multiplying, you add exponents. And then I can multiply my f times f squared. When I do that, remember the exponent here is 1, so I'm doing 1 plus 2, which would give me f cubed. The last thing I want to point out with this is notice here those coefficients, that 3 times -3, you are multiplying those. The thing that confuses students sometimes is they want to add everything. You are only adding your exponents. This is a multiplication problem though. We are doing 3 times -3, not 3 plus -3. I've got one last one here for you to try. If I wanted to multiply that, I would say -2 times 5, which is -10. M times m to the 5th power would give me m to the 6th power. There's a total of 1 plus 5, 6 m's you're multiplying together. And then the same thing for n, I'm going to add, and I get n to the 11th power. Now all of these problems here had multiplication in common. There are more exponent rules. The next 2 we're going to look at have to do with when you are dividing monomials. We're going to start off with something you guys already know. I'm going to start off with 5 divided by 5. We know that 5 divided by 5 is 1. What about x divided by x? In class, I usually hear either 1 or x. Remember what this means. A variable just represents an unknown number. So this is saying that number you don't know, divide it by itself. You could pick any number for x if you wanted to. Let's pretend x is 3. This would say 3 divided by 3. If x is 100, it would say 100 divided by 100. It doesn't matter what number I put there. If you're dividing it by the same number, it's going to leave you with 1. If I said x divided by x equals x, that's like saying 3 divided by 3 is 3, which isn't true. That's why the answer is 1 and not x. Now if I continue that pattern, what about a squared divided by a squared? Well, the same idea. I'm taking something and dividing it by itself. It's going to give me 1. This next rule we have says anything divided by itself equals 1. Most of us already know that with numbers, right? Anytime you're dividing a number by itself, it equals 1. This is just to show you that same thing is true with variables. Variables are numbers. We're just representing it with a letter, but it's the same idea. If you're dividing anything by itself, it's going to equal 1. Well, this is great and all, but what if you're not dividing the same thing? All of these problems, all of these division problems, I was dividing the same thing. What if I'm dividing different things? Like 4 to the 5th power divided by 4 cubed, or x to the 4th power divided by x squared. Well, similarly to what we did with the multiplying exponent rule, there's a rule to do these problems, but I'm not going to tell you. Instead, we're going to do the first two, see if we notice a pattern, and then use this third one to confirm our pattern to come up with that rule. So this first one here, I've got 4 to the 5th power divided by 4 cubed. What does that look like if I wanted to write it all out? Well, 4 to the 5th power says 4 times 4 times 4 times 4 times 4. And then 4 cubed is 4 times 4 times 4. Remember, our goal is to simplify. What could I do here to simplify? Well, I see 4 divided by 4. We know 4 divided by 4 is 1, so those 4's cancel. 4 divided by 4, 1, cancel. 4 divided by 4, 1, cancel. I could multiply these together, but remember we're looking for a pattern with exponents. So instead of saying 4 times 4, if I wanted to say that with an exponent, it would be 4 squared. Now this problem here, the base was a number. What if the base was a variable? Well, same idea. X to the 4th power is x times x times x times x. X squared is x times x. So just like over here, I'm going to see that x divided by x gives me 1, so it cancels. X divided by x gives me 1, so it cancels. That just leaves me with x times x, or I could write that as x squared. Now remember, our goal, our purpose of doing this is we want to see if you notice a pattern with the exponents so that we can confirm if that pattern could be a rule. What do you notice about the exponents here and here? What could we do to skip this middle step to get to our answer? Well, there's always someone in class who says, oh, look, they're all squared. Do you think they're always going to be squared? No, it's going to depend on what the exponents of these other two are. The other thing sometimes people will say is, I think maybe we could subtract. I see that 5 minus 3 gives me 2. 4 minus 2 gives me 2. Let's go with that. Maybe our exponent rule is subtraction. If the rule is subtraction, what would this final answer be? Well, 5 minus 1, there's a 1 there as the exponent, would leave me with 4. So I'm thinking this one here is y to the 4th power. Let's confirm by writing it out like the others. Y to the 5th power is y times y times y times y times y. Y is just y. So that one of those would cancel, and it leaves me with 4. It leaves me with y multiplied by itself 4 times, which is y to the 4th power. So if you said subtraction earlier, you are correct. That is our next exponent rule. It says when you divide the same base, so again, notice the y's are the same, the x's are the same, the 4's are the same. When you're dividing the same base, you subtract the exponents. Again, I really think it's important for you to see this so that you're not just memorizing this random rule. It's going to stick in your brain a lot better if you know where that rule came from. Now that you've seen this introduction to dividing monomials and the exponent rule that goes with it, I've got these two here for you to try. The first one says t to the 10th power divided by t to the 5th power. The next one says p to the 4th power divided by p. And the second part to that is prove your answer to number 5 is correct. If I asked you, well, how do you know that? No, you wouldn't just say like, oh, because the teacher told me to do that. How could you prove to me that this is correct? Well, we're using that exponent rule that says you're subtracting exponents in division problems. So this would be t to the 5th power. If I subtract here, that would be p cubed. If I wanted you to prove to me that's correct, you could do exactly what we were doing earlier. You could say, well, p to the 4th power is p times itself 4 times. P is p. And so one of those would cancel out, and you're left with 3 p's multiplied together, which is p cubed. Now, just like the multiplying monomial problems, we're starting small, but let's make these a little more fun with coefficients and more variables, all that fun stuff. The idea for doing these is similar to the multiplying monomials. Just like when we were multiplying two monomials with a lot of stuff going on, you looked for what you could multiply together. Same idea here. If If I'm dividing two monomials, I want to see what can I divide together. So for this first problem here, I could say, well, 4 divided by 2 gives me 2. And then when I divide those x's, x to the 6th power divided by x, I can divide x's and subtract my exponents, which would leave me with x to the 5th power. Try doing that same process for number 8. What would that leave you with? Well, here there's nothing for me to divide the 7 by, so one way you can think of it is just copying down the 7. The other way people think of it is if you don't see a coefficient, we know it's a 1, so you can also think of it as 7 divided by 1 gives you 7. Either way, you get 7. When you divide your y's, if I subtract those exponents, I have 2 minus 1. I don't see that 1. 2 minus 1 is 1, so I get the exponent 1. Now that might look weird to you. Hopefully it looks weird to you. The reason it looks weird is because this is y to the 1st power, but we saw right here you don't see the exponent 1. The same thing is true then about writing it. You don't need to write the exponent 1. And then the last part, when you're dividing your z's, if you subtract the exponents, it's going to leave you with 2. So we get 7yz squared. Now for this last one, there's something fun that happens in this last one. Go ahead and try number 9. Well, for number 9, we've got negative 12 divided by 3. That leaves me with negative 4. When I divide my a's, I subtract 7 minus 2, which gives me the exponent 5. When I divide my b's, notice I'm dividing b to the 7th power by itself. That goes back to that exponent rule we learned earlier. When you're dividing something by itself, it's going to give you 1. Now you could write times 1, but anything times 1 is itself. What that means is there are no b in the answer. The biggest mistake for this problem is students want to write a b there. There's a couple ways you can reason why that's incorrect. One is because we know if you write a b, the exponent is 1. So that's like you telling me 7 minus 7 equals 1, which it doesn't. The other way is go back to what this means. Remember, I'm always saying go back to what this means. B to the 7th power means you're writing b times itself 7 times. 3, 6, 7. We're dividing by that same exact thing. So what that's going to mean is that every single one of those b's is going to cancel out, which means you're left with no b's in your answer. Be on the lookout if you're dividing something by itself. At this point, you know 3 exponent rules. You know that when you are multiplying two monomials, you do what with the exponents? You add them. And you know when you're dividing two monomials, you do what with the exponents? You subtract them. And then anytime you're dividing something by itself, like in that last problem, it's going to give you 1. There is one last division problem for you to try. Here we've got negative 5, j cubed, k. The 15 divided by the negative 3 gives me negative 5. And then when I subtract my exponents, 4 minus 1 gives me 3. And 2 minus 1 gives me 1. And I don't have to write the exponent 1. The last rule we're going to look at is what you do when you have a monomial raised to a power, or where you have something with an exponent raised to another exponent. Now, just like the other ones, I'm going to use this as an example to help us figure out where this rule is coming from. And in order to do that, I want to go back to what squaring something actually means. If I give you something like 5 squared, what does that mean? Well, 5 squared means 5 times 5. What about a squared? Well, a squared means a times a. What about smiley face squared? Usually that's where people laugh and say, okay, I get it. Smiley face times smiley face. Good, I want you to get it. Anytime you're squaring something, all it means is that you're taking whatever is being squared and you're multiplying it by itself. So if we use that same idea, pretend this right here is your smiley face. X cubed squared means what? Well, it means x cubed times x cubed. You're taking what's being squared and multiplying it by itself. Now before, when we had an exponent raised to an exponent, we haven't seen what that rule is yet, But here, I've changed it to a multiplication problem. We do know what the rule is for multiplication. When you're multiplying two monomials together, you add those exponents, which would give me x to the 6th power. Now this wasn't too bad. If the exponent here is squared, all I have to do is write it twice. Why do I need a rule for that? Well, I could have changed that problem to be x cubed to the 20th power. What would that mean? Well, it would mean x cubed times x cubed times x cubed times x cubed 20 times. I don't want to have to write that down. So just like all of these problems, there is an exponent rule that you could use to get from this to this without having to write out what it looks like. Do you see what that rule is? Well, in this problem here, I see the 3 and the 2. I see that I could multiply these exponents to get to our answer here. That means for something like this, I don't have to write x cubed times itself 20 times. I could just say, well, 3 times 20 gives me 60, so that's x to the 60th power. That's the last rule we've got for today. That last rule says when you raise a monomial to a power, you multiply the exponents. Now that we've got that last rule, I've got these two here for you to try. The first one says y squared raised to the 4th power. The second one says x cubed raised to the 7th power. In both of these, you're just multiplying your exponents. So you would get y to the 8th power and x to the 21st power. Now, just like all of these problems, we're not going to stop here. We can make these even more fun by adding in more variables and coefficients. Just like all of these problems, the idea is the same. You're going to use whatever that rule is that we learned and apply it to multiple things. So for this problem here, I've got x to the 4th power, y squared, all raised to the 4th power. In this problem, we are going to apply this exponent, that 4, to x to the 4th power and to y squared. So what that means we're going to do is to get our final exponent for x, we're going to do 4 times 4, which gives me 16. And then for y, I'm going to do 2 times 4, which gives me 8. You could always write this out if you wanted 4 times. But remember, the purpose of exponent rules is to save you from having to write it out each time and just get you to that answer there immediately. Now this next one here, we've got 3z to the 6th power all squared. What would the answer for that one be? Well, to get our exponent for z, I want to do 6 times 2, which gives me 12. The biggest mistake students make on these is they say, okay, 6 times 2 is 12, and then 3 times 2 is 6. The problem with that is because this does not say 3 times 2. It says 3 squared. It says 3 squared, which doesn't mean 3 times 2. It means 3 times 3, which gives us 9. You want to be real careful with those exponents and those coefficients. It's the same thing we've been seeing before. You're always doing something different with the coefficient than you are with the exponents. But for this one I think is the one that tricks students the most. The other way you can reason about it, I know these can be sometimes tedious, but you can always go back to what it looks like if we wrote it out as a multiplication problem. And that helps you see 3 times 3. That's where that 9's coming from. I've got one last one. Why don't you try number 6? Number 6, similar to this, says 2 cubed. 2 cubed means 2 times 2 times 2, which is 8. Don't forget about that a there. This says a cubed, which is literally a cubed. Remember, there's that exponent 1 there. 1 times 3 gives you 3. And then for your b, we multiply 8 times 3, and we get b to the 24th power. The last part for this is these two here for you to try. We've got mn to the 7th power, all raised to the 5th power. And then 5c cubed d squared, all squared. For this first one, make sure you didn't forget about the m. It would be m to the 5th power, n to the 35th power, because we're multiplying those exponents. Here, make sure you did 5 squared. 5 squared means 5 times 5, which is 25. and then c to the 6th power, d to the 4th power. These are the last examples we've got. Before you leave the video, I want to real quickly review all these exponent rules you learned. The first one said if you are multiplying two monomials together, what do you do with the exponents? You add them. The next rule we learned is if you are dividing a monomial by itself, it equals 1. Then we learned if you are dividing two monomials, what do you do with the exponents? You subtract. And then our last one we learned is if you have a monomial raised to an exponent, what do? You multiply. I would either write those words down or write these examples down, whichever way you think, in your notes, because I think the math is simple, right? All we're doing today is adding, subtracting, multiplying, but it's real easy to mix up what you need to do for each of these problems. So I personally like to think of it with examples. Thank you so much for watching this. We are going to be using all of the stuff we learned in this video on exponent rules to help us tomorrow when we multiply and divide polynomials. So get excited. Thanks. Bye.